So today we'll be doing stress analysis over a beam. So you'll see deflection of beams. It's an H beam this time. So I have the drawing ready in that case, but I will show you firstly the steps to get components from Fusion, and then we move on to the Inventor. Also, for those who didn't take kinematics, um, you may use this video, which is a tutorial I made earlier to create an assembly. Okay, it's after the 27th minute. I discuss how you like make an assembly. So if you see here, this crank slider mechanism was just 4 components, and in that video we show you how to make them an assembly if you need it in your mechanics simulation and stress analysis. Um, okay, I'll open Fusion now. I will show you the file format that you should end up with. So what you can do is whatever the drawing you have, whatever software you're drawing on, you can bring it onto Fusion, since Fusion supports a lot of formats that many other drawings softwares or CAD softwares do not support. So basically what I did for this, it's already in my, okay, let's get it out. So it was HBM. Yeah, so it was hbm.igs. What I did is open here, open from my computer, and I selected HBM IGS. Okay. Now I didn't take this HBM as is, and it's very like the dimensions did not um, suit me well. So what I did is I extruded and cut the dimensions. I will skip over these parts and jump right to the final file I ended up with. Okay, so I'll go to my saved files, and one thing in Fusion, save it on the cloud so you can export it to the Inventor format. It will ask you Aslam. Anyway, see if I'm trying to do export. Okay, and this is an Autodesk Inventor format, IBT or IAM. Here it will give you an error. This file should be saved on your cloud, not on the file. Sorry, on your desktop or your computer. It should be saved on the cloud. Because Fusion has a lot of cloud integrations. Yani, most of the computing happens outside of Fusion, not on it. Okay. So this is my projects and my files. This is the HBeam after editing. Okay, it's floating there. So I made it, instead of that very long beam, I made it a 2-meter beam. Now, this is what I want to emphasize on before importing. So just quick summary of what we did. We imported a drawing into Fusion. We edited the drawing on Fusion, and now we are in the exporting stage. Before exporting, you have to check units. Okay, I think it's lagging. 1 second. Yeah. I usually do it by typing units, but it's not working this time. So what I'll do is right click on the drawing itself. So here you can see that the form, it's already using millimeters. I would recommend millimeters since in Inventor the main options are millimeters and inches. So even if your drawing is in centimeters or meters, convert it to millimeters. If we go to inspect, the length here is given to be 2 meters, okay? Just for your reference. So now we will select this object and hit export, okay? And you select the IPT IAM. Now this will take a bit of time depending on the action. Since I have done it before, it's completed very quickly. This usually takes like 2 to 5 minutes. And it will generate some zip file. You'll find 3 files. This is an already assembled file including 2 things, the surface and the body itself. Okay? And this is the surface alone, and this is the body alone. I would recommend if you are importing and exporting to just use the body itself. And for us, it will be only part 4, we'll not import all of this. Do you want me to show you what will happen if you like open this one or this one alone? Yes. Okay, okay. So we'll export all of them then. So here I open the first file, which is an IAM file. Okay. Let me show you file by file. So I'll go to Inventor. This is what you'll see when you open Inventor Home. You'll see this page when you open Inventor. Okay, I'll click open. This is the HBM. This is IAM file. It looks like this. Okay. Uh, so what you'll see here is we have 2 things. Part 4, which is the body, and this surface, the cross-sectional area. Okay, as a surface. It's highlighted here. See? Okay. See, it's highlighted in this green. Okay, and the part is the body itself. So that's why we're using the part alone. We're not using the surfaces. I will close this one and open other files just to show you what will happen. This is HBM file. It's only the surface. You can know its surface from this symbol, the orange one. Okay, and if we open the last file which we'll work on, okay, let's zoom out. This is the part itself. Okay, I'll show you another way to import, especially if you have multiple components. So we close everything. This is home. I'll open in simply file and start placing components. Since we are going to work only with the body parts, so I'll select part 4 and open it. It will give you an option to place it. Place it anywhere since it's the first part. Okay, and it will change the view to show it. You can place multiple beams. If you have, like, let's say an overhead crane, it will have 2 beams and again gantry system over it. Okay, but for us, we only need 1 beam just to show you the stress analysis. So now we have an assembly. In this case, it's only 1 part, but for your project, it might be multiple parts. Okay. Now, before we start doing anything, we'll go and check the units again in Inventor. So you go to Tools, Application Options, File, Configure Default Template. You go to Millimeters and ISO. Okay. Why ISO? Because we want also the forces to be in Newton, the pressure to be in Pascal, and so on. And the stresses to be in Pascal and megapascal also. because um, this is the US system, the NSI, and the ISO is the metric system that you are used to. Okay, so if you have your loads in the standard units or the US units, you can keep it as is and keep the inches as well. But you have to be consistent between your drawing and importing it and the analysis that you'll be doing. Okay, so for me, I'm doing everything in the metric system. I'll do these changes. Okay, overwrite, apply, and close. Then you'll go to environments, okay, and you'll go to stress analysis, the second option here. Okay, all options are off now until you press create study. Here, since okay, it's still in inches here. Um, you'll continue with the static analysis. You don't have to change any of the options for now, okay? Since your loading is also a simple static loading, right? Do you have any dynamic loading in your project? I will go double check the units thingy. Yeah, it is recorded, but not on Teams. I'll share it through YouTube link. Let's go back and see what happened. Environment, no analysis, create study. I'll try again, then we can move on. I want to cover the important stuff. I'll try to restart the project. No, save. Yeah, see, it is in millimeters. Okay. But also, see, these now are now similar to the AutoCAD. See here in Fusion. Okay. So now they are the similar axis. So if this was horizontal, this will be horizontal as well. Previously, these axes were following the non-ISO convention, but everything now is uniform. Okay, so better you change these options before you start importing things. Go to tools. If you are at the home page, go to tools, application options, and you change it here right away before you begin importing anything. طيب, let's go back to our project. I'm gonna rotate it actually. I don't want to go back to Fusion. Let me find a way to change it quickly here. No. So just import the horizontal beam and we'll get back to the stress analysis. It's required in the project to do it on Inventor. Plus, you'll have so many options that we'll cover now, and you'll see why we need Inventor or Answers to do it. Okay. So now we have the beam horizontal. You go to Environment, Stress Analysis, and create a study. Now everything is in millimeters. I mean metric system units. You can leave this option unchecked if you have simple load, okay, and a kind of simple design, right? Not if all the components are perfectly crafted like here and are simple. What I mean by perfectly crafted is you excluded these files and you only took the components that are necessary for the assembly. You can leave these unchecked, okay, and you just move on, okay, the next step. Now all these options are open now in the analysis. You have to go step by step in these, either in this ribbon or in this panels, okay. Go from left to right or right to left. What will happen here is first is the material. You have to assign material. And this goes to many things. You have to do your own research on what materials are used in your, let's say, crane or gantry or whatever you're simulating. Or if you have like a website that sells this equipment, you can go check there what material they are using for their equipment. Okay, so since it's a beam and steel is common material for beams, we will select steel. So you'll go to assign. You have these three options. The original material you don't have to change as okay. You go to the new material that you want to change, and you can go and see all of these materials. Okay, we select here steel and move on. And ANSYS, if you are working with ANSYS, it's automatically selected to structural steel, okay, by default. And if you have any different material, you have to change it also as well. But here the default is generic material, and I don't know what are the properties of that material. So we have to change it in the beginning. Now we change to steel. See here now there is a plus sign that wasn't there, and so you make sure that you finish these steps. Then we add constraints. Now, depending on the body or the equipment or the part you are analyzing, this will be selected. Yani, not like the dynamic simulation where you have to have a ground. You could have 4 pins or 2 pins, and that will make uh, enough constraints to simulate. In our case, we'll make it a welded beam, so it's welded from both sides. When we say welded, we'll only select the edges. Okay, and this is the option that we have now. When you want to set a fixed constraint, it gives you the option to select the edge or the surface. We will try both. Let's try now the surface, then we can, okay, you can select these edges, all of them, if it's like a welded joint, for example. Okay, but for me, I'll select the surface right away. Okay, and I will make it fixed from a fixed beam. Okay, so you can press shift and the middle scroll wheel to change the view, and you can hit the home button to complete it. Now, when you are selecting the faces, you don't have to hold control or anything. You just select them. Okay, I'll select them again. So one click here, and one click on this surface, and that's it. And you apply. Now, these 2 points, since we hit apply once for them, they will be assigned one fixed constraint. So if you delete this entry, you'll delete both of them. Now, if I want to assign more fixed uh, parts, let's say these two faces, and I apply it, there's another fixed constraint. If I don't want it, I just delete this one, and it will keep the previous one. See, the previous one is still kept and still considered to be fixed. So this will be fixed. We can try, if we have time, to make one fixed free beam, and we'll see what happens. Now we go into the loading. In case of beams, if it's a very long beam, it can have deflection due to its weight. So you can add gravity. Okay. And you can apply forces or pressure. Pressure, if you apply it takes the whole surface into account. Okay, and it's generated by 4 arrows on this software. So let's say 100 megapascal, apply and cancel. Then you can apply force as well. You can apply so many loads as much as you need. Say 10 newtons. I'll select this surface and apply it. Okay. Now you can switch the direction, and if it's a complex load, you can give it the components as well. See, now it's at an angle. If the force is at an angle, but it's not in our case. It's loaded on top, so I'll not use it. But do you want me to keep it for the analysis? It's gonna get results anyway. Do I keep it or remove it, Shabab? Okay, let's change the color to differentiate between. Uh, Usually red is meant for the gravity, but let's keep it. You know that it's an external force applied on. See, now in this case, it's not applied on the whole surface since it's force. It's applied at the middle of the surface, okay, at a point. And this is something really nice when compared to Inventor. Sorry, when compared to ANSYS. Because in ANSYS, if you want to apply a force at the middle, you have in your drawing to draw a line in the middle, and when you come here you select edge and you select that line to apply the load in the middle. So this is a really simple or simplest way to applying loads in Inventor when compared to ANSYS. ANSYS has other advantages that we'll go over. Okay, when we discuss the mesh or what's the mesh, ANSYS has so many more options and verification options to check for the mesh. Okay. Then we have something called contacts. Let me close this. Next is contacts. طبعا for us here, let's apply it. There is no contacts to be applied since it's one part. Okay, and this part is usually cast. So there is no contacts. In case of any other complex components, I will share a video with a complex component that goes over the same step from YouTube as well. Where contacts, he generated like, let's say 60 contacts on a really small part. Okay, and you can assign this contact manually. Are they bonded? Are they welded? Is it a bolt? Is it a spring contact? Okay, this depends on your assembly. So for this beam, there's no contacts. Then we move on to something called mesh. This mesh, uh, basically, this is not very accurate what I'm going to say, but it's just to get the idea for you. And we are computing this load on these small elements. These are called elements, and combination of these elements is a mesh. So we are dividing this entire part into smaller elements. Okay, the smaller the more accurate because we represent more smaller area. Okay, if the element is small, we represent smaller quantity. If you have more, we get more accurate. Now you can customize the mesh in these settings. I'll change the size. For now, it's 0.1 on average. So this part is kind of uniform, so you might see that most of them are the same size. But see here, for example, in these curves, these elements are much smaller. Okay, I'll discuss the elements more on, but let me show you what happens when we decrease the size. Update mesh. See now, when you zoom on, the elements are much smaller, and we are expecting more accurate results. Now, what's the trade-off? The trade-off is the more elements you have, the longer computing time for the system. So you have to engineer or not engineer, to know how many elements are enough for you. How small you have to go for the elements. In this tutorial, I will stick to the main default mesh. Then I will change to a smaller mesh to show you the difference in the results, and we'll show you something called convergence tool, where we let the software run multiple times and decide on the size of elements that we see the smallest change in results. So let's say these results give us 200 megapascal in stress. Then I refine it, it gives us 230. I refine it again. Refine means smaller elements. It becomes 260. So the changes are significant and we cannot ignore it. But I refined it again for the fourth time, and the changes is from 260 to 261. So in that case, we know that the mesh we used at the third time is good enough. And this is what the conversion tool is doing. So to repeat and keep reducing the elements until the results converge. And here in this button, you can select the criteria and how many iterations it can go through. Okay, so let's select 5. Okay, we'll go there after the initial analysis. We'll cover the manual change of elements and the convergence tool. So now going from left to right, we are left out with something with the simulation. Okay, so you press simulate, then run, and this is what will happen to your beam under these loadings: pressure on top and a side force. These here are shown the von Mises stresses in megapascal. This is the minimum, this is the maximum. See here is the unit and here is the values. The one this value is very high actually. You can see also the displacement, which areas has had the most displacement. So at the top here we see 102 millimeters in displacement. Right. What I want you now to memorize is this number, 102 and 5. Let's write in the chat. 102.5 millimeters. Now, what I will do is I will change the mesh into the smaller one and let's see what happens to the results. Simulate and run. See now, it took much longer time to compute the next one because of the smaller elements. And when we have smaller elements, we have way more elements to compute. So it requires more processing power. Now it changed from 102 to 107.5. Okay, let's change again and see what happens. Uh, I think this is very small and it will take so much time, but let's try it. Now, in your finite element course, doing this alone, just making the elements much smaller is not enough. Actually, you have to do it as an engineer. You will see where are stress concentration areas, and you refine the mesh there, make it smaller in that stress concentration area. And in the other areas that do not have much stress, you can leave the element as big as it could be, and you don't need very accurate results in a low stress area. Okay. So the more complex the geometry, you want to refine the mesh there. There is a refinement option here. This second option. I will cancel it because this will take a lot of time. Yes, cancel step. Close. Here is a simple. See here in a curved area, you can refine the mesh and leave the mesh elsewhere the original size. And this is very helpful in increasing accuracy, but keeping the total number of elements in check. Now, I'll run the same analysis using the convergence tool. I'll run for 5 iterations. I want a change, let's say, of 10%, 10%, not on displacement, on von Mises stresses. You can change what results you want them to converge. See here, you can decide on displacement. You want the displacement to converge or the stress to converge. Usually all of them converge within the same iteration, but not necessarily. And then we simulate and run again. when you if you want to view it, you have to to update it. But when you hit run, it automatically see now it's computing the mesh. It's updating the mesh according to the last changes. So you're right. Thanks for the reminder. We didn't change the. We didn't bring it back to the original size. It was 0.1. See now, okay, it computed the first mesh very quickly. Let's see what happened. So after the fourth iteration, the von Mises stresses were in within 10% of variance. So it was in 1.1% of the previous value. So it stopped. As long as it is uh, more than 10, it will keep iterating till it reaches the maximum iteration. We set it to 5, now it's 4. Let me see if we can view the new mesh. Okay, so it did refinement on these areas and kept these areas uh, as the original size. What I like to do is I reduce it a little bit here, okay, generally speaking, okay, and I run also the conversions tool. Before it was 19,634, which the material definitely break at that point, at that stress level. I will actually change the constraint, change the loading to have more realistic results. Now, the finer the mesh you start with, the more time it will take to compute each run or each iteration for the convergence tool as well. So here it converges on the fifth iteration. Now, one last option I didn't cover is how much is the refinement on each iteration. You can change this value and default it to 0.75. Now this was 19,000. Now it's 38 after the convergence. See here, it was 19,000. Now it's 38,000. And these numbers are unbelievably high. So let's put some realistic loads. I'll delete these two loads. Um, let's put force. How much you want? Let's put 100 kilonewtons. On this surface, and direction is connect, apply, close. If you are doing the same thing on ANSYS, keep in mind the student version of ANSYS, the free one, is up to 100,000 elements. If you go above that, the student version will not allow you to do the stress analysis on it. But it seems here that it's not limited, it's not the case on Inventor, which is good. So here we're left with 128 megapascal, which is at least less than the yield strength of steel, right? Right. One question I have for you: does 100 kilonewton will generate this deformation? Like if we have this part actually, what do you think? Yeah, the length here is 2 meters. Yeah, exactly. Yes. Yeah. There is some exaggeration here, just to show you the effect. If you want to see the actual effect of this load, you hit the actual. طيب, now it seems that it is the 100 kilonewton didn't affect anything. But if you go to displacement, double click, it is 0.35 millimeters. That's the maximum displacement that we got. So if you zoom in very close, you will see that the black line is a little bit above exactly this value, 0.35 millimeters. Okay, let's increase the load just to have. So actually, this is what will happen to the part. The maximum location, which is at the center, will change by 0.3 millimeters, and that's it. This is at zero point 0.5 exaggeration, and this is at 1, and you can keep increasing. Basically, the smaller the deformation, the more exaggerated you want it to be, and just to see it, uh, let's say, more prominently, I would say. One more thing, or the last thing I want to cover, is the viewing of your results. Okay, there's this button called report. You change the image, let's say this. You'll select the view. Now I selected the side view. You will go to the studies, and I will select to print sorry, the results only, and we'll hit OK. So it will keep the view I selected. When I hit the button report, it will save the view. So if I did this in the home view, it will print that, and this is what it will print. It will print the loading that you are having on the component. It will print the maximum and the minimum value of each of the study parameters: x displacement, y displacement, z displacement, strain, and xx, the von Mises stresses, and so on. And all of these will be shown here. So if you want, let's say, displacement, this is the x displacement, this is the y displacement, this is the z displacement. Okay, these are the most useful things basically in your entire stress analysis. You have to generate this report. Now you can change the format. If we hit report, let's say the format, and you can make it a PDF so you can attach it to your appendix in the report. Um, let's get it back to 0.5. Okay. See if I'm in a home position, I'll print again. Yes, I would like to overwrite it. See, all the photos now are in that view. Okay, and it's showing you also the constraint that you are applying on the system. You have to include the conversions as well. Okay, but this conversion was done for the displacement, and for 5 iterations it didn't change at all from 0.359. But for the von Mises stresses, it started at the initial mesh with 39 megapascal, and we ended up with 128 megapascal. So make sure you're using the convergence tool. 5 iterations is what you should aim for. Okay, if it's taking more than 5 iterations, something is wrong, either in your initial mesh size or the refinement. You're not doing enough refinements. We usually do refinements at the sharp edges, curved edges, like the one here shown here. Okay, and stress concentration area. Okay, and we sometimes increase the mesh only in the area of interest. Yani we are not interested in the failure here, مثلا. We're interested in the failure in this location. We increase the mesh there to get more accurate results. And when we refine it, this will get more refined, and this will get more refined as well in the convergence, but not the same ratio. It's always will be more refined in the area where you select this local mesh control. I'll return to the original size just to show you the refinement tool. So if I want to refine this edge only, okay. Um, Selecting the edge, not the face. That's it. Let's make it. It was 0.1. How much you want to make it? 0.05. Now update mesh. Okay, it failed. I'm not sure about this error. If you get it in your problem, we'll fix it together. But I'm not sure about it right now. Because this is the steps you do. You select the face or the edge you want to refine, and it will get refined. طيب, let's try a different or similar number. Uh, let's make it 0.1. Still failing. Yeah, I'm not sure about why it's failing. Okay, do you want me to run different deflection of beams? I said I want to do the fixed free. Do you want to see it, or do you want me to import anything else? Like if you have a drawing or something, you can import it and work on it instead. But this is the point of stress analysis. We want to see the displacement, the safety factor, the von Mises stresses, and so on. يا شباب. Yep. Thanks for reminding me. Yeah. Okay, let's run the analysis to have results, because the results here, see this, it's not calculated yet. So yeah, this is really important. It's called prop. You select the point that you want the value to be shown exactly. Yani, if you see this gradient, we know that at this point we are in this region between 102 and 128. Yeah, but we don't know exactly how much the stress here is. So there is a prop. You select the point exactly, and we'll show you the exact value. Okay, so this one, okay, it is this one actually, the prop. And if you want to hide and unhide the labels, you press this one. So let's take the stress at this point. So the when my stress is there, where is this? Okay, at this point is 70. At this point, it is 115, and you can hide them and unhide them using this. You can move them as well if they are overlapping. Now, if you go to displacement, for the same points, they will change. You can add another prop here, let's say. And yeah, you can add as many as you want. Okay, any other questions? What's the error you're getting? Okay, let's save this recording. Can you send it in the meantime?